This question belongs to the topic theory of machines from subtopic mechanisms. Here is the question. A 4-bar mechanism is made up of links of length 100, 200, 300 and 350 mm. If the 350 mm link is fixed, the number of links that can rotate fully is dash. Okay. Here is the 4-bar mechanism given to you. Okay. So here is this is the link 100 mm, link 200, 300 and 350. So if it is 300, and this will be 350 mm. Okay. Okay. Now this is the 4-bar mechanism given with 350 mm link fixed. So now if you apply the Grashoff's law, that is S plus L less than or equal to P plus Q, that is summation of other links. This is for the class 1 mechanism. This is for the class 1 mechanisms, right? So here the first here the shortest link is 100 mm. Here this is the shortest link, this is the shortest link, and this is the longest link. These are other links P and Q. So here if I write, here it will be 100 plus 350, 100 plus 350 less than 200 plus 300. Yes, it is a class 1 mechanism. Now here if you see, the link, the fixed link is the link adjacent to shortest. Link adjacent to shortest is fixed. Link adjacent to shortest is fixed. Okay, shortest link is the fixed link. The result will be crank rocker. Result you will get is crank rocker mechanism. So in a crank rocker mechanism, you will have only one rotating link. Link 2, or that is 100 mm link, will be undergoing 360 degree rotation. Okay, this is the end of the answer. This question belongs to the topic theory of machines from the subtopic mechanisms. For an Oldham coupling used between the two shafts, which among the following statements are correct? First statement, torsional load is transferred along the shaft axis. Second one, the velocity ratio of 1:2 between the shaft is obtained without using gears. Third option, bending load is transferred to the shaft axis. Fourth option, that is rotation is transferred along the shaft axis. So here Oldham coupling is used when you have eccentricity within the shaft axis. Oldham coupling is used when you have the eccentricity between the shaft axis. So here it is not, here the velocity ratio, there is no change in velocity ratio. Whatever the velocity of the input shaft is there, the same velocity will be there for the output shaft. Okay, so the torque and the velocity is transferred along the shaft axis. Okay, so as per this, it will be option B, that is 1 and 4. Statement 1 and 4 are correct statements. That is, torsional load is transferred along the shaft axis as well as the rotation is transferred. Okay, this is the end of the answer. This question belongs to the topic theory of machines from subtopic dynamic analysis of mechanisms. Here is the question. A slider crank mechanism is shown in figure. At some instant, the crank angle is 45 degrees and force of 40 Newton is acting towards left on the slider. The length of the crank is 30 mm and the connecting rod is 70 mm. Ignoring the effect of gravity, friction and inertial forces, the magnitude of crankshaft torque needed to keep the mechanism in equilibrium is dash. Okay, here is the mechanism given to you, having crank length 30 mm and length of the connecting rod is 70 mm, crank angle is 45 degrees and torque is asking you to calculate. So now here this is some angle theta or crank angle theta, and this is the phi is the angle made by the connecting rod with the line of stroke, and here is the force 40 Newton exerted on the, or 40 Newton basically is the piston effort. 40 Newton is basically the piston effort. Okay, FP is equals to 40 Newton. Okay, now here on the point B you have a force of 40 Newton. Okay, and this is thrust on the connecting rod, that is FQ. This is angle phi. Okay, this is angle phi. So FQ is equals to 400 by cos phi. From here, if I write FQ cos phi is equals to 400, which means FQ is equals to 400 by cos phi. And for calculating phi, I need this relation, that is R sin theta is equals to L sin phi. R sin theta is equals to L sin phi. This opposite side is equal for this triangle and the big triangle. Okay, so I can write this as 30 into sin 45. 30 into sin 45 is equals to L is 70 into sin phi, that is phi is equals to, upon solving this you will get phi is equals to 17.6 degrees. 17.6 degrees. Okay, so now this is the force on the connecting rod. This is the force on the connecting rod. Now coming to point A, the force same FQ. This will be the same force FQ, or instead of marking FQ here, I can write here also FQ. Okay, so one force will be directed along the radius, that is FR. One force will be directed along the radius, that is FR, and another force will be perpendicular to the radius, or called as tangential force. Okay, so this angle here it is, this angle is 180 minus of theta plus phi. 180 minus of theta plus phi, the other angle. So this, if I say this to be as FQ, then this will be theta plus phi. This will be theta plus phi. So now FT is equals to FQ into sine of theta plus phi, and now torque is equals to FT into R. That is equal to, torque is equals to, FT is what? FT is FQ sine phi. FQ is what? 400 by cos phi. So 400 by cos phi is 17.6 degrees. 400 by cos of, sorry, it is not 400, it is 40 newtons. Sorry, it is 40 newtons. 40 by cos 17.6 degrees and into sine of 45 plus 17.6 degrees into the radius of the crank radius is 30 mm. 30 into 10 power minus 3. So now upon solving this entire answer, you will get 1.17 Newton meters of torque. Okay, 1.17 Newton meters of torque. Okay, this is the end of the answer. This question belongs to the topic theory of machines from the subtopic gear trains. Okay, here is the question. An epicyclic gear train shown in figure below. The number of teeth on A, B, and D are 20, 30 and 20 respectively. The gear C has 80 teeth on the inner surface and the 100 teeth on the outer surface. If the carrier arm is fixed and the sun gear A rotates with 300 rpm in clockwise direction, then the rpm of D in clockwise direction is dash. Okay, so now here it will, if A is rotating in clockwise direction, B will be in anti-clock. If B is in anti-clock, C will be in anti-clock because of internal gearing, and D will be in clockwise direction. So it will be in the direction of, same sense as that of A. Now here the arm is fixed, velocity of the arm will be 0 and the teeth of A is 20, teeth of B is 30, teeth of D is 20. Internal teeth on C is 80 and external teeth on C is 100. He is asking you to compute what is the speed of D, given that speed of A is 300 rpm. Now A is in mesh with B, so the pitch line velocity of A and B will be same, and ATA is equals to NBTB, and B is in directly mesh with C, so I can write inner circumference of the gear is in mesh. So pitch line velocity at the inner circumference will be same, not at the outer circumference. So now I can equate these two, that is NA is equals to 300 into TA is 200, that is NC is not known, TC is 80, so which means NC will be equal to 75 rpm. NC equal to 75 rpm. Right, now similarly the outer circumference of the wheel is in mesh with gear D, so NCTCI, it has to be NCTCO into is equals to NDTD is equals to NDTD. ND is equals to NC is 75, NCO is 100, TCO is 100, TCO is 100 divided by TD. TD is equal to 20, so this will be 25 is 100 and 75 5 is 375 rotations per minute, okay, which is option C. Is the end of the answer. This question belongs to the topic vibrations. Okay, so here is the question. The equation of the motion for the spring mass system excited by a harmonic force is given by mx double dot plus kx equal to f cos omega t, where m is the mass and k is the stiffness and f is the force amplitude and omega is angular frequency of excitation. Resonance occurs when omega equal to dash. Okay, this is a straightforward question. Okay, straightforward question. Mx double dot plus kx is equals to f cos of omega t. So natural frequency, he is asking you to compute the natural frequency or at the natural frequency. When the excitation frequency equals natural frequency, then only the resonance will occur. So this will be k by m times of x is equals to f by m cos of omega t. Okay, so this part root over k by m or omega square is equals to k by m. So here it is omega n is equals to root over k by m is the natural frequency or the frequency at which resonance will occur, or also you can call it as a critical speed. Okay, critical speed or yes, critical angular frequency also you can call. So in case this is expressed in terms of radians per second, see here, since he is asking you to calculate in terms of omega, it has to be in radians per second. If he is asking you to calculate or compute in terms of hertz, this will be divided by 2 pi times of root over k by m. So here the computation is only limited to omega n. So option will be D, that is root over k by m. Right? This is the end of the answer. This question belongs to the topic vibrations from the subtopic forced vibrations. Okay, a machine of mass m equal to 200 kg is supported on two mounts, each mount of stiffness 10 kilonewton per meter. Machine is subjected to an external force of force in Newton, that is f of t equal to 50 cos 5t, assuming that only vertical translatory motion. The magnitude of dynamic force transmitted to each mount is dash. Okay, so now here the force equation is given to you, or this time varying force that is applied, that is equal to f of t is equals to 50 cos 5t. 50 cos 5t is the force applied. 50 cos 5t is the force applied. And next is the stiffness given to you. Stiffness is 10 kilonewton per meter. Okay, stiffness is 10 kilonewton per meter, and mass is given as 200 kgs. Mass is given as 200 kgs. Now the natural frequency omega n will be equal to root over, here you have two springs arranged in parallel, so stiffness will be directly equal to 2k times of m, that is equal to 20,000 divided by 20,000 by 200, that is equal to 20,000 by 200, that is equal to 100. So this will be 10 radian per second will be the natural frequency. 10 radian per second will be the natural frequency. Right, next is he's asking you to calculate what is the force transmitted to each mount. Okay, force transmitted to each mount. Here the damping is 0, so damping factor will be also equal to 0. Damping is absent, right? So now you recall that relation, that is transmissibility ratio, that is epsilon is equals to f of t, that is force transmitted by force applied. Force transmitted by force applied is equals to root over 1 plus 2 zeta r whole square plus this will be by root over 1 minus r square whole square plus 2 zeta r whole square. Okay, so now this is where zeta is the ratio of the damping and r is the free ratio of frequency of excitation to natural frequency, where R is the ratio of frequency of excitation to natural frequency. Okay, so now here I can write it as, this is here f of t, here zeta is equals to 0, so which means f of t is by f is equals to 1 by 1 minus square, okay, whole square. Here it will cancel since you are removing the under root. Okay, so here it is f of t by omega is omega by omega n, that is omega is equal to 5. Okay, omega is equals to 5 and omega n is equals to 10, that is 0.5. Okay, this is 0.5. f of t by f is equals to 1 minus 1 by 1 minus 0.5 square, 1 minus 0.5 square. So this I can write it as f of t, force transmitted is not known, f is 50. This can be written as 1 minus 1 by 4 is 1 minus 1 by 4 is 3 by 4. This is 3 by 4. 1 minus 1 by 4 is 3 by 4. So this will be 200 by 3, which is approximately equal to 66.66 newtons. Yes, F is given in newtons, so this will be 66.66 newtons. So these two springs will be sharing a force of 66.66. So load on each spring will be equal to, that is 66.66 divided by 2, that is 33.33 newtons. Okay, so this is the end of the answer.